Let's remove them and take the power up a notch to 1.1. Now we have two lines on the negative side. What's going on here? Let's draw in just one curve for x of magnitude 1, again starting at -1 and going all the way back around to -1. We started with -1 and ended with -1, but somehow our curve didn't connect back to itself. How is this possible? I'm sure you've heard of the famous Euler's identity, the one that states that e to the I pi equals -1. This is actually a special case of representing a complex number in terms of magnitude and an angle. The full form would look like this. So a complex number z given by this expression would be m distance away from the origin at a theta angle in respect to the real axis, which means its real and imaginary parts could be obtained trigonometrically like this. The famous special form of Euler's identity is just a complex number of magnitude 1 and an angle of pi radians, halfway around the circle. And here's a catch, we can hit that same spot where the number -1 lies with an angle of pi, but also with an angle of 3 pi or any odd number of increments of pi. And we can go the other way around too. Remember, I've shown you that when we pick the complex values of x we put into our function, we start at -1 and travel this way around to get back to -1 again. The way these values are generated behind the scene is that we're ranging the angle from -pi to pi. The round bracket on the left just means that we're only including values strictly larger than -pi, because this ensures that every point is represented only once. Why this range in particular? It follows certain conventions in complex arithmetic, but long story short, you could say it's the range that gives us the nearest of the infinitely many representations of a complex number we can get in this form. We reach all angles with an overall minimum amount of travel from the angle of 0. Now let's look at raising a complex number in this form to a power. The exponent is going to distribute. It's going to affect the magnitude normally like it would any real number, and it's going to multiply the angle. Now we can finally examine the case of our function. We were raising -1 to the 1.1 power. We'll do it first as the angle of -pi. Okay, the magnitude we can get rid of because 1 to the power of anything is just 1, and we'll bring the 1.1 next to pi so the angle is easier to comprehend. Now we do the same for the angle of +pi. These two expressions end up in different places on the complex plane and escape our initial constrained range. One overshoots a bit into the positive imaginary side, and one into the negative. Neither of those two numbers are real, they are both detached from the real line. If we were drawing the graph of the function in an ordinary way, these values, and generally all the values for negative inputs of x, would simply not be shown. But we're not drawing the graph of the function. We are instead, remember, showing numbers of the form z equals x plus f of xi on the complex plane. And these numbers exist for any input of x we can think of, at least for functions we've considered so far. In the specific case of our function, this results in lines on the negative side slightly deflected from each other. Alright, enough background. Let's fill in some more curves and slowly crank the power the rest of the way up to 2. Okay, let's look at that again, rolling back to 1. And again to 2. We can see the results for negative x values rejoin each other as we reach the next integer power, and in doing so wrapping the span between the negative and positive sides over itself to form the focal point. Let's push this model a bit further. How does x squared become x cubed? Looks like the focus that already existed survives, and another one forms through the same wrapping back onto itself motion. But there's a problem. There is no such thing as a focus for the graph of x cubed, let alone two such points. This is where the geometric definition of a focus and the behavior of our system go their separate ways. But never mind, it looks interesting, so why don't we crank the power up some more? Let's go to x to the 4th power, and then to 5th. Right, it's making less and less sense to think of these points as foci. We get them in areas where the graph of the function bends, but also elsewhere seemingly unrelated to what the graph is doing. But if we add lower power terms to the polynomial so that we express all the possible extrema, the points will travel to align with them. I increase the range and density of the curves so you can better see these features. Pause here if you'd like to take a closer look. This phenomenon of curves splitting between integer powers and joining at them has to do with roots. Any non-integer power is really a combination of a root and raising to a power, like we've seen earlier. Let's write real numbers a bit more explicitly using Euler's identity. Positive real numbers can be represented by any angle that is an even multiple of pi, because all of those are on the real line on the positive side of 0. 2 pi is one full revolution. Likewise, negative real numbers can have any angle that is an odd multiple of pi. Multiplying those angles by a specific integer always yields one definitive location on the circle, no matter what choice of k we make. If we multiply an odd number by 3, it will always be odd, no matter which odd number we chose. And if we multiply an even number by any integer at all, it will stay even, reflecting the fact that positive numbers stay positive under any integer power. We have multiple representations of the same numbers, but we get the same result under exponentiation with integers. However, if we multiply those different angle representations by a fraction, we get different results, the most familiar of which is the case of 1/2, the square root. The 1/2 will make the period cycle just 1 pi, which means it will sometimes be even and positive, and sometimes odd and negative. We get the two roots of 1, and the same happens for any positive number. There's quite a lot of nuance here, and we'll explore it by driving our graphing method further down, below the first power. Let's again first just go down a notch, to 0.9. Here we see a similar separation happening like before, but this time the lines are not crossing over each other, they are instead opening up a gap between them. Let's follow this down to 0.5. 1/2, the square root. That gives us half of a parabola turned on its side. The lines for negative values of x got compressed onto the negative side of the real axis, with a bit sticking out on the positive side. And that bit is exactly touching the focus of this half-drawn sideways parabola. The proper focus is back. How about we add the negated version of this function in as well and complete the picture? Right, the parabola is now fully reconstructed along with the same shape of curves we got for x squared. And we also got this extra bit that looks like the handle of a pitchfork. Of course, this is not the actual graph of the function you see on the screen. We're doing this z-value shenanigans and cherry-picking which parts of it to show. I'm gonna leave it up to you to ponder on why we get the pitchfork handle here. Meanwhile, we continue our descent down the powers, and things get even more interesting at our next stop, 1/3, or the cube root. Just doing what we've done before, we get to this picture. But there's something off here. This function does actually have real outputs for negative values of x. If we drew it the regular way, it would look like this, a perfect and complete inverse of x cubed. That's because within the reals, there is only one cube root of a number, and it's always the same sign as the number itself. So why do we get this other picture instead? We have to look at complex exponentiation again to find that out. To keep it simple, we'll again just consider the general positive and negative cases for the number 1 expressed using Euler's identity. It works the same for other magnitudes. First, we have the positive case, e to the power of 2k pi. We raise that to the 1/3 power, which gives us 2/3 k pi. As we iterate k, we get the following angles. And then they repeat. Only one of them, this one, is a real number, and it's positive. For the negative case, we'll get 2/3 k plus 1/3 all times pi. As we iterate k, that will give us these three angles, of which again only one is real, this time negative. The way we draw our graph, the positive side gets represented by an angle of 0 that stays 0, So we get positive outputs for positive inputs and everything just looks normal. But on the negative side, we're coming in with angles of minus pi and pi, which give us the positive and negative 1/3 pi angles, the two complex ones. That hints at there being two more versions of the graph we could draw to complete the picture, just like we had an extra one to complete the square root sideways parabola. We can get these missing two by multiplying the function with a unit turned 1/3 of the way around the circle, like this, and then one more time, like this. So let's draw them, one by one separately at first. This is the one we already saw. And then we get this one, which completes the real valued graph and gives us the continuation of the two negative sides. But notice how the curves for complex values just end up in a vacuum, not connecting to any of the thicker lines. Their new home has been defined by the previous stage. Here's both of them together. Finally, we get this one that for some reason just contains the funny separated lines without any part of the real graph. These are in fact the solutions we've already seen for complex values of f of x, they just all appear in the opposite order. And here's all three together. I know, this looks messy, there's too much going on in this picture. But there's an amazing elegance hiding behind it. First, let's just notice that we've again fully reconstructed the shape of the colored curves for x cubed. And now let's just focus on the thicker lines depicting results for the real valued inputs. What we're actually looking at are three copies of the x cubed shape pressed onto the complex plane in a manner similar to what flowers look like when they're physically pressed onto a page of a book. To show you what I mean by that, we'll briefly change perspective. Let me hide the graphs, and we'll go back to the familiar coordinate system where the horizontal axis represents x and the vertical f of x. Now we slightly upgrade it. We'll declare the vertical axis to be just the real component of f of x, and add another axis going directly towards you for the imaginary component of f of x. We can get away with using 3 dimensions here because we're only considering real valued inputs for x, so it's a mapping of 1 dimension to 2. And now we draw our 3 graphs again. This is what they look like in the space we've created. We can look at the whole resulting shape as 3 cubic curves. Turning the coordinate system around to face straight down the x-axis, we reveal the 3 planes these curves occupy. We see that these planes are offset from each other by 1/3 of the way around the circle. Note that we were measuring the angles going from the positive side of one curve to the positive side of another. Now, when we look at our simplified model again, we have a better idea what the shapes we're seeing actually represent. We've just compressed these rotations into a visual deformation, a sort of fake perspective in 2 dimensions. We're not seeing the true picture, but there's an amazing amount of symmetry preserved. These 3 curves, when inverted, represent graphs of 3 regular cubic functions, and all 3 of these functions, when run through the same z expression we've used this whole time, yield the exact same shape, with the quasi-focus points appearing in the same places. So, we've made a long pit stop at the 3rd root, but it's time to move on. We're going to put multivaluedness behind us again to have a simpler image to look at, and make our way towards the next interesting power, 0. Of course, that's just a straight line through 1. Let's look at the journey between the power of 1 and 0 again. 2 simple straight lines separated by the thick woods of multivalued roots in between them. And as we approach the power of 0, we can see a discontinuity form, the dreaded 0 to the power of 0. Going even just the tiniest bit under 0th power results in values approaching the vertical axis exploding to infinity. So we have this situation right over the power of 0, and this right under it. There is something remarkable happening at the singularity when both values are exactly 0, and to understand it, we'll consider the limits as we approach it from different directions. The most commonly considered ones are x to the power of 0, our function itself, as x goes to 0 from the positive and negative sides, which both work out unsurprisingly to 1. The same happens if we simultaneously approach 0 in both base and exponent. The negative side limit only exists if we allow approaching from complex numbers, but it's there. If we fix the base to 0 and approach the 0th power from the positive side, we also unsurprisingly get 0. But if we plug any negative number in the exponent, forget the limit, we get this peculiar mathematical object called complex infinity. Its formally used symbol is just the regular infinity we're used to, but I find this confusing because it can easily be mistaken for positive infinity. Wolfram Alpha uses a notation with a tilde over it to make it more distinct, and I will adopt that. So what is this beast? To understand it, we need to consider how 0 works in the complex world. In the reals, 0 is the only number that isn't either positive or negative. And in the complex world, since there are infinitely many directions, this ambiguity encompasses all of them. 0 is basically a circle of radius 0 in the complex plane. Its direction is undetermined, which in some sense means we need to consider them all when operating on it. Raising this number to any negative power turns it into division by 0, which is commonly left undefined, but within a special set called the extended complex numbers, that is, complex numbers with this omnidirectional infinity added to it, this operation is actually allowed since it yields a single definitive answer. That means that our singularity goes through a kind of Big Bang. The infinitely small circle of 0 instantly becomes an infinitely large circle, a place where all complex numbers, regardless of the direction they were headed out in, will meet. Keep that in mind as we travel down to the negative 1 power. At the end of this journey, we get a familiar function x to the negative 1 power, better known as 1 over x, which has this property of looping back from infinity around the x value of 0. Well, now you know where Pac-Man went and where he's coming back from. Along the way, we're passing multi-valued roots, just like we did on the positive side, and finally we formed the two foci of the hyperbola, in a similar way like the single focus showed up for the parabola. There's a lot more to say about these phenomena, but I'm going to leave that for another time. This inverted version of the behavior we've seen on the positive side continues on down to the lower powers, like this. I suspect all this stopping and restarting we've done might have felt a bit frustrating, so what I want to do now is to just let the animation run from -4, where we currently stand, back up to 5, so you can see the whole story come together. And since we're done explaining, we'll crank up the range and resolution to make it more pretty. Here we go. I hope you like this journey. If you'd like to play around with this model, I've included links to Desmos graphs where you can fiddle around with the parameters to get a feeling for how this model behaves. Links in the description. As a bonus, let me show you some other notable examples visualized this way. The exponential function, x to its own power, and back over constant 1 to my favorite, Gaussian function, the normal distribution. And let's enhance it a bit. And then we go back over the exponential function, and we draw e to the ix, which we remember to be cosine x plus I sine x, so if we just stake out the I sine, we get the cosine on its own. Thank you so much for watching. I hope you enjoyed and learned something new. I'm curious to know what you think of the approach taken here, what questions it inspires, so please leave a comment and let me know.